Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving here today, as it is every day here in my virtual classroom. Step on inside. We're going to do section 3.3 in the Big Ideas Math Integrated Math 1 textbook. This is on function notation. This is going to be something that looks a little weird to you if it's brand new. We're going to have to, unfortunately, accept it for what it is, and I'll make it very easy, and it has very good use for you as well. And listen, it's something that doesn't go away. It's something that's going to stay with your math life no matter what you do. So we're just going to have to accept it for what it is, and that's not a problem. That's not a problem. I'll be your holding hand on this guide through the solutions. Speaking of which, this video goes, I think, only to problem number 36. So hopefully it's also a shorter one. You might need to use your calculator for this. We'll see if we have to graph. If so, I'll attach graph paper below, and it'll be in PDF down below with this textbook page set on section 3.3, along with the timestamps and the playlist for IM1 you can find down below. Without further ado, I'm going to go ahead and get started with the lecture. If you want to find the problem set, go to the timestamps down below. You will learn to use function notation to evaluate and interpret functions. Evaluate just means come up with the number for. Use function notation to solve and graph functions. Okay, graphing will be had, and solve real-life problems using function notation. Now, function notation is the core vocabulary here. Quadrant, I think, has to do with graphs, and linear function we just learned in the last section. So what the heck is function notation? Well, you know that a linear function can be written in the form y equals mx plus b. That was our big talking point last time. By naming a linear function f, you can also write the function using function notation, where it says this right here. Now, this is going to look a little weird for you right here. They wrote this. They wrote an f and an x in parentheses. I want to state this right now. This does not say f times x. This does not say f times x. Excuse me. I believe they'll tell you. Oh, actually, they say it right here. Oh, they said that right here too. The notation f of x is read as the value of f at x, or the way I say it, f of x. It does not mean f times x. Parentheses to you, I know, means multiplication. Not in this way. They're stating that y is a function of x, in this case, in a linear equation. This is replacing y, which means this means y. The notation f of x is another name for y. Do you have to use the letter f? No, that's what they use by default. Why? I don't know. Function starts with f. Normally, they also go alphabetically upward if they want to use any other form of it. They're going to use it at some point. They might use g of x. They might use h of x. They might use p of x, q of x, r of x. These are just other ways to indicate different y values based on your x value. I hope I haven't confused you yet. We're just stating this is a way to replace y. And again, it doesn't say f times x. If f is a function and x is in its domain, then f of x represents the output of f corresponding to the input x. What does that mean? It means the same thing that y does. You plug in an x, you get out a y. But with function notation, the benefit, by the way, here's the g or h thing that they state right here. You can use other letters such as g or h. The benefit of f of x, function notation, is that you get to see what input you are using to get that y value. So for example, evaluate a function. Evaluate f of x equals negative 4x plus 7 when x equals 2 and when x equals negative 2. So here's what we're going to do. We have our function right here. Now, there are going to be a lot of times, and if you get me an IM2, IM3, you watch my videos, you're going to hear me say this a lot. Anytime I see f of x, I just straight up say y all the time. I don't change it to a y, but you know where it says f of x equals negative 4x plus 7? You can also say y equals negative 4x plus 7. And you'll see me literally do this all the time. Y equals negative 4x plus 7. I literally, to me, this just says y in my head anyway. So we're totally good. Anyway, f of x equals negative 4x plus 7. Here's what they're going to do. They say evaluate for this when x equals 2. So what are they going to do? Substitute 2 for x. Now, what are they going to do on this side? Absolutely nothing. In fact, they don't even write anything down here, absolutely nothing the other time, because this is just a repeat of the same thing over and over. They're not solving for f as in divide both sides by 2. There's nothing like that. They are evaluating this side by substituting 2 for x. We've been doing that the last couple sections. We've been plugging in numbers for x and getting values out for y. That's what they're doing here. They substitute 2 in for x. This is multiplication. This is the expression. Negative 4 times 2 plus 7 is negative 1. Therefore, they're saying f of 2 equals negative 1. Don't continue solving. You're done on that thing. You've evaluated what y is when x equals 2. Therefore, and they didn't really mention this. Well, they did. They said when x equals 2, f of x equals negative 1. What this really means is When x is 2, y is -1. That's a point on your graph. And again, I'm over-explaining something to try and oversimplify it. I want to make sure it makes total sense that we haven't changed anything, guys. This is still y. This is still y. But it's much easier to say find f of 2 instead of find y when x equals 2, especially if you have to do multiple of them. So it's a shorthand way of doing that, but they mean the exact same thing. The other thing this f of x thing does, two more good benefits of this f of x stuff that I really like, function notation, I should say. Number one, you can differentiate from different y's. You can have an f of x, g of x, h of x, like I said, to represent different y's, different functions in the same system. Number two, you know it's a function. You know it's a function. So you know that y is the dependent variable. It depends on what x is, and you know what to plug in for x. So there are a lot of benefits to this thing. Now let's substitute -2. F of -2 equals -4 times, substitute -2 for x, plus 7, which becomes 15. So there's another point on the graph that's -2, 15. So as I've already spoken, about 6 minutes on something that someone else could have spent a minute on, f of x means the same thing as y. So does q of x, so does t of x. Heck, x doesn't have to be your variable. You're going to do some things later in life where you do v of t. Find the velocity at time t, and you go -16t squared plus 32t minus 4, something like that. This can be your equation. And they said find v of 8. Find the velocity at time 8. And that's what you do. You substitute 8 for t, and then you find v. So there are a lot of things for that we do with it that is helpful for us. By the way, the word notation just means the way that something's written. Have you heard of scientific notation? Right? You've heard of that. You'll hear later about inverse notation, probably in IM2. Notation just means the way that something's written. Function notation, this is the way that it's written. Now that I've said all that, we probably get to speed up a little bit. Let's interpret function notation. Let f of t, oh, here's a change in variable. Let f of t be the outside temperature t hours after 6 a.m. Again, this could just be y. Let y be the outside temperature t hours after 6 a.m. Okay? Explain the meaning of each statement. F of 0 equals 58. That means you're substituting 0 for t, and the output that you're getting right here, 58, is the amount of degrees that the temperature is outside in degrees Fahrenheit. The initial value of the function is 58. Oh, initial because this is time 0. So at time 0, the initial value at time 0, the temperature is 58 degrees at 6 a.m. 6 times 6. T is the number of hours. 6 hours later, the temperature is now n degrees outside. I don't know what that means, but it's n degrees Fahrenheit. Even they say the same thing. There's an input, and that's your output. We don't have an equation we're plugging it in for, but this is what they're talking about. Here's your input. There's your output. We can input 3 for time. We can input 9 for time. What they're stating is 3 hours later at 9 a.m., 3 hours after 6 a.m. is 9 a.m. At 9 a.m., the temperature outside, the output, is less than, it's cooler than the temperature 9 hours after 6 a.m., which would be at 3 p.m. So at 9 a.m., the temperature is cooler than at 3 p.m. If I plugged in 3 for t, came up with spit out my temperature, that's going to be less than the temperature 9 hours later. So here's what they say. The temperature at 9 a.m. is less than the temperature at 3 p.m. So we'll interpret that together as we do more problems, but there was nothing to actually plug in. It's just that t was the input, f of t was your output. Using function notation to solve and graph. Solving for the independent variable. Okay, this one's a little bit backwards of things. For h of x equals this equation here, 2/3 x minus 5. By the way, that's y equals mx plus b form. Find the value of x for which h of x equals -7. Now, this is flipped over. This does not say find h of -7. We're not substituting -7 for x. We're substituting -7 for y, for h of x. So instead of h of x being right here, we're substituting -7. From there, you solve for x like you know how to. I'm going to let the work speak for itself. But when y is -7, x is -3, given this output, let's find the input. So there's a point on the graph that's -3, -7. But it's substituting this entire thing for that. This entire thing might as well say y, though, right? Y equals -7, substitute it. So again, this just means y. It doesn't matter whether they say h of x, f of t, f of x, whatever it is. It just means y. It just means y. Graph a linear function in function notation. Here's a y equals mx plus b form equation. We're going to substitute values for x and get values out for y. Hey, it's no different than what we just did in the last section. Let me move my face. And every value of x that you substitute, we can do f of negative 2. 2 times negative 2 is negative 4 plus 5 is 1. Boom, there's your y value. F of negative 1. 2 times negative 1 is negative 2 plus 5 is 3. Boom. F of 0. 2 times 0 plus 5 is 5. 2 times 1 plus 5 is 7. 2 times 2 plus 5 is 9. So these are the f of x values. This is f of negative 2, f of negative 1, f of 0, f of 1, and f of 2. They represent xy values. That's what they're stating right here. I've been stating that a couple times. They plot the points and they graph. Now, why do we draw a line through this? We're going to, by default, assume that every graph that we draw is continuous. There's nothing that states that there's a domain restriction on this. Notice that they also substituted negative values and positive values. This isn't a word problem. This is something where x can represent any number in the domain, all real numbers. And the range happens to look to be all real numbers, but that's not part of what we're talking about right now. Function notation just means the same thing. Substitute x's, get out y's. And I'm probably speaking, I don't know if I'm speaking poorly on it by over speaking about it, because I'm trying to keep it simple. I want to keep reminding you that this is what it is. It's like when new calculus and pre-calculus students learn about this thing called derivative and instantaneous rate of change. They don't know that it just means slope, which is a much more basic concept. Okay. Modeling with mathematics, a word problem. Let's see what we got. Good old first flight. The graph shows the number of miles a helicopter is from its destination after X hours on its first flight. On its second flight, the helicopter travels 50 miles farther and increases its speed by 25 miles per hour. The function f of x equals 350 minus 125x represents the second flight, where f of x is the number of miles the helicopter is from its destination after X hours. Okay, so which flight takes less time? Explain. We got a graph for the first flight, and the second flight we have an equation right here. It states which flight takes less time. Here we can tell the first flight takes 3 hours, period. We're 300 miles away at time 0. 3 hours later, boom, we hit that. So we already know first flight is 3 hours. Second flight is all about, remember, they said the helicopter's destination, y, or f of x, x hours after its flight, and here's our equation. So f of x represents how far away we are from our destination. We want to find out for what value of x gets our destination gets us 0 miles from our destination. We want to substitute 0 for y, for f of x. We want to make an equation that says 0 equals blah, blah, blah for that situation. So you have that option. You can set it equal to 0 and solve. It doesn't look like that's what they did, though. Okay. It looks like they did this later, so I'll show you that in a bit. Actually, I'll show you that right now. So they substitute 0 when f of x equals 0, x is 3 on the first flight. When f of x equals 0, x apparently is slightly less than 3. Now, they did it through a graph. I didn't know we were supposed to graph it. So what they do for the graph, they plugged in values for x and got values out for y. When x is 0, y is 350. When x is 1, f of 1 is 225, f of 2 is 100, f of 3 is negative 25. So somewhere between hour 2 and hour 3, we apparently hit our destination. This doesn't mean that you flew past your destination here. It means we probably stop our domain once we hit a y value of 0 in this situation. See, I would have preferred doing exactly this right here. Substitute 0 for y and solve for x. That's my personal preference. Did they say graph it? They didn't tell you to graph it. So they said make a plan and graph it. I don't think I necessarily would have done that, personally, especially since they said we know how to solve these things, but we have to know what the 0 represents in the context, and I think they now just told us. All right, that finishes the lecture portion. Through time, if you had trouble with that, hopefully we can still make more sense of it. F of x is just another way to say y, guys. F of x is just your output. And in a lot of situations, I prefer it. And I hope you will too later. All right, vocabulary and core concept check. Complete the sentence. When you write the function y equals 2x plus 10 as f of x equals 2x plus 10, you are using what's called function notation. What changed? Y turned into f of x. How come? Because f of x is y. For functions, f of x is y. Reasoning. Your height can be represented by a function h where the input is your age. What does h of 14 represent? The input is your age. We are going to input 14 into some equation. I don't know what the equation is. I don't care. But based on that input, we can get an output of height. So if input's your age at 14 years old, h of 14 represents your height at 14 years old. 14 represents age. H of 14 represents output of height for that age. They don't show like feet or centimeters or anything like that. All right, guys, we're going to do the problem set. We are going up to number 36, 3 through 36. So hold on tight. This should be pretty clean, quick, and contained. Not really contained because we're going to use function notation for the rest of our lives after this. So you don't have to, but you're going to see it for every other walk of math hereafter. Probably not much in geometry. Whoopsie, I need to go to the actual... I'm here. I just need to switch slides. There we go. Okay, so without further ado, let's go ahead and get started. We have numbers 3 through 10, where we evaluate the function when x equals -2, 0, and 5 for this function. Guys, we're going straight into, the section's called function notation, but I'm going straight into function notation right here. It's always x equals -2, 0, and 5. So what am I going to do? I want to take f of -2, f of 0, and f of 5. What does this mean? It means find the value of y when x is -2, find the value of y when x is 0, find the value of y when x is 5. And that's it. We substitute these for x. That's it. -2 plus 6 is... No! -2 plus 6 is 4. 0 plus 6 is 6. And 5 plus 6 is 11. I did something where I was reading ahead on this problem and started to write the answer. This is f of -2, f of 0, f of 5. It was that easy. Wait, that's all you do? Yes. Wait, haven't we done this before? Yes. We're just learning the notation, the way that it's written. We're not learning anything new, process-wise. We're given the new appearance of something and using it. G of x equals 3x. Do we have to use f of x? No, we can use g of x. Let's do g of -2, g of 0, and g of 5. That means we substitute -2 for x here. Use your parentheses for substitution when in doubt, especially multiplication. 3 times 0 and 3 times 5. 3 times -2 is -6. 3 times 0 is 0. 3 times 5 is 15. Those are the values. Now, what we found, again, we found the value of y when x is -2. We found the value of y when x is 0. We found the value of y when x is 5. That's what we found. Number 5. H of x equals -2x plus 9. This is where you might have to do more work. It depends on the problem. This is your y equals mx plus b form, by the way, to remind you of this because it's going to keep showing up. Y equals mx plus b. These are linear functions that we're looking at, and this is exactly that. Remember, h of x means y. All right, this time I'm going to go kind of more vertical here. Let's do h of -2, which is -2 times -2 plus 9, which is 4 plus 9, which is 13. We have h of 0 is -2 times 0 plus 9, which is 0 plus 9, which is 9. And then we have h of 5, which is -2 times 5 plus 9, which is -10 plus 9, which is -1. And I don't know if I'm going to spend time doing all those steps each time. I can do the intermediate step, like -2 times 2, -2 is 4. 4 plus 9 is 13, and I can just write from here to here. Just depends on the problem, but just reminding you of what we're doing on it. Number 6, we have r of x. Yeah, do these have to be f of x? No, they only used f of x the first time. How dare they? They were all about f of x to begin with, right? Notice we're not doing anything on the left side of our equation other than stating what we're substituting. So r of -2. We're just showing, let's find out what y is when x is -2. We're not going to do anything else here. We're leaving it. That's it. That's it. Now here you got to be careful. We have a negative in front of the x, and the x is a negative value. So it looks like that. Opposite of -2 is 2, and 2 minus 7 is -5. R of 0 is the opposite of 0 minus 7, which is 0 minus 7. That's -7. We all know this. You already know what it is. And whoops, R of 5, that's opposite of 5 minus 7. -5 minus 7 is -12. I don't like my scattered work like that. I got to organize it better. Let's see if I can do that on this one. P of x equals -3 plus 4x. Now, we can leave it looking like that. I don't like its look as much just because I'm OCD like that. Maybe I prefer writing it as y equals mx plus b form, 4x minus 3. It's whatever. It doesn't matter. Let's see if we can fit these a little bit better here. P of 2 is 4 times -2 minus 3. That's -8 minus 3, or -11, right? P of 0 is 4 times 0 minus 3, and 0 minus 3 is -3. And P of 5 is 4 times 5 minus 3. 20 minus 3 is 17. So there's another version of that. I hope that that kind of cleans things up a little more. So we can fit more down below. I can't really fit much more on the lines on that page. So let's go to number 8 on B of x. (18 minus 0.5x). Now for the uncertain, 0.5 is also 1/2. You can write it like this as well. This would still be negative. I'll leave it as negative 0.5, but get used to seeing things more as fractions in this form than as decimals, unless it's a word problem. Or this problem, apparently. Plus 18. Now, do I have to write it like this? No. Does it help or hurt this way? It could hurt, but it's not going to hurt too much. All right, b of negative 2. This one is fine. Negative 0.5 times negative 2. Stay away from your calculators. That's a positive 1, and that's 19. B of 0. What you're going to get used to, I don't know if you've noticed this, what you're going to get used to is multiplying this thing by 0. Clearly, no, multiplying something by 0 wipes it out, but guys, this is going to be 18. I'm going to start doing this now. This negative 0.5 times 0 is 0, plus 18 is 18. As long as we're in that slope intercept, the y equals mx plus b form, then you're good on just how that stands like that. B of 5 is, this is probably where the decimal's kind of helpful to use. I'll keep it in decimal form. This is negative 2.5 plus 18, or 18 minus 2.5, which is probably where we were better off using the other form, and that's 15.5. So notice how I'm using function notation to evaluate these y values given the x's. You're like, I don't see a y anywhere here. And I don't know why they don't say y of x. Y is a function of x. I'm not sure. I guess they need to make sure that if we're going to replace it with y, that we don't actually use y. Now, this is definitely one of those problems where I'd really love to clean up what's inside there, right? We simplify sides of an equation. I got 12 minus 5 is 7. It's a positive 7. And I still got this negative 2x. If I write in mx plus b form, that's it. So v of negative 2 is negative 2 times negative 2 plus 7. 4 plus 7 gives us 11. And that has nothing to do with 11. Gives us 11. V of 0, if you've learned it here mentally, this will give you 7. Because negative 2 times 0 gets wiped out. And then v of, I guess I ran out of room there. V of 5 is negative 2 times 5 plus 7, which is negative 10 plus 7, or negative 3. All right, number 10, n of x. And again, something to clean up here. Equals negative 1 minus x plus 4. Or negative 1 plus 4 is 3, so we can say negative x plus 3. That's our y equals mx plus b form at least. Let's do n of negative 2. The opposite of negative 2 is 2, and 2 plus 3 is 5. N of 0 will give you 3 because that part wipes out, and n of 5 is opposite of 5, boom, plus 3, which is negative 2. Okay. So, yeah, see, for me, that's not only faster than saying find y when x equals, and for some of us, we would have said, okay, let's plug in negative 2, y equals, and y equals, and y equals. Now we can't differentiate one from the other. Here I can clearly tell what my output is based on my input. X, y, x, y. They definitely have benefits here. Number 11, interpreting function notation. Let C of t be the number of customers in a restaurant t hours after 8 a.m., That means when t is 0, hold on a second, we get to interpret it. I take it back. Explain the meaning of each statement. So part A says C of 0 equals 0. What they're stating is at hour 0, because t is the input, right? C of t is the thing. At hour 0, time 0, there are 0 customers. Input, 0 hours, output, 0 customers. Now, hour 0 is 0 hours after 8 a.m. So at 8 a.m., there aren't any customers in the restaurant. I want to make it sound as English-like as possible. All right, that is part A. Part B. C of 3 equals C of 8. Now, this means that at hour 3, we have a certain number of customers. I don't know how many. Neither do you. Who cares? Maybe 0. At hour 8, we have a certain number of customers as well. At hour 3 and hour 8, there are the same number of customers in the restaurant. That's what that means. What's 3 hours after 8 a.m.? It's 11 a.m. 8 hours after 8 a.m. is 4 p.m. At 11 a.m. and 4 p.m., there are the same number, that the number of customers in the restaurant is the same. I can't spell, I'm sorry. I promise I'm really good at this on my own accord. I really should practice it right now. Part C. C of n equals, C of n equals 29. Now remember, n is your input, the number of hours after 6 a.m. So I just got to say it that way. N hours after 6 a.m., 29 is the output. That's how many customers are in the restaurant. So n hours after 6 a.m., there are 29 customers in the restaurant. And then part D says C of 13 is less than C of 12. Is 13 less than 12? No. Is hour 13 before hour 12? No. We're talking about C of 13, the number of customers at hour 13 versus the number of customers at hour 12. And this states that there are less customers in the 13th hour, which would be 9 p.m. So at 9 p.m., there are less customers in the restaurant than at 8 p.m. 8 p.m. is 12 hours after 8 a.m. That's how I kind of did that math a little faster. Okay, number 12. Let h of x be the percent of U.S. households with internet use X years after 1980. Explain the meaning of each statement. So more of the same as the last one. It's a different context, though, and we're going to have to use that. This is a good way of making sense of function notation. We're substituting, we're inputting, but we're not using an actual equation. That doesn't mean this information isn't relevant to what we do. Here's our input, here's our output. This is the number of years after 1980. This is the year 2003. This is the percent of households with internet. So in the year 2003, because that's 23 years after 1980, in 2003, 55% of households have internet. I mean, I don't know if that's normal or not. That it seems low, but again, 2003 was a different time. We still had dial-up. I think this is around the time that my family switched to cable modem stuff. H of 4 equals K. K is just some unknown value, right? But it's still a percentage. So 4 years after 1980, oh yeah, this is probably just unknown information. In 1984, In 1984, K percent of customers, of households had internet. I should probably say had for these. So that's 4 years after 1980. Part C. Part C says H of 27 is greater than or equal to 61. That doesn't say H of 61. It just says 61 as a number. 61 represents a percentage on its own, not 61 years after a certain thing. 27 is 27 years after 1980, which is 2007. So in 2007, what they're stating is there were at least 61% of households with internet. So in 2007, at least, I wish you saw my setup. I have to go around my microphone thing when I type. That's a part of why this is having trouble. At least 61% of households had internet. 61% or more, right? Part D says, this is a little bit. H of 17 plus H of 21 is about H of 29. So even though this question is a lot like the previous one as far as what you're doing, they're asking things differently, for sure. So H of 17 would be 1997. H of 21 would be 2001. We're not adding those years. We're adding the percentage of customers, of households that had internet in those years. So the sum of the percentage of households with internet in the years 1997 and 2001 combined is approximately the same as the percentage of households with internet in 2009. In 2009, you can see this drastic increase over time as more people get internet, stuff like that. And that's kind of how that one's working. Okay, number 13 to 18. Find the value of x so that the function has the given value. Okay, this one's a little opposite here. This is equivalent to what we had to do in the lecture. This says h of x equals negative 7x, and we have to find out for what x value you get an h of x of 63. This is the exact same, guys, and I'm only going to write it this time, of y equals negative 7x, where y equals 63. We are not substituting 63 for x. This is not an input. We're substituting 63 for y, and we're finding out what value of x that is. So what are we doing? 63 equals negative 7x. We're going back, folks, to pretty easy solving linear equations here. We divide both sides by negative 7, and we get an x value of negative 9. When when y is 63, that output gives you an input, is from an input of negative 9. All right, that's the solution there. So we're solving for x. We're plugging it into this thing that you hate. This number's going away for this number here. And we're solving for x. So use your good old algebra methods for these ones here. So number 14, we have t of x equals 3x. I'm sorry. T of x equals 3x, and t of x equals 24. Literally, it says t of x equals this, t of x equals that. Well, then this must equal that, right? 24. 24 equals 3x. It's been another long day. Divide both sides by 3, and now we're getting x equals 8. Okay? I don't have much to say on these problems other than reminding you how function notation works, what y is, how it represents, what we're substituting. We are given our output, and we're trying to find our input. M of x is 4x plus 15. By the way, these are y equals mx plus b form. They're really getting you in the groove now with it. And these are all in function notation, which means they're functions. And they are. They're linear functions. And we're given the output of 7. And we're trying to find what input gives us an output of 7. And we work backwards algebraically to do so. So this is 4x equals negative 8. And if you divide both sides by 4 here, you get x equals negative 2. Now, all the things that we're solving here are as difficult as something you would have seen from section... Was it 1.3 by the time we were doing? No, this is like section 1.2, solving multi-step equations, but not equations with variables on both sides, because we're substituting for this variable y equals 6x minus 12, and y equals 18. Mr. Robinson, that doesn't say y, that says k times x. No, it doesn't. It says k of x. K times x. This is 6 times x, and we're substituting this for that. Y and k of x are the same thing, right? But that doesn't say k times x. I wonder for error analysis if they're going to do something like that. I kind of hope they do, that they have something set up, because I can show you exactly what they'll do in another situation where they'd solve, and if they don't, like if they don't show you, I'm going to, and I'm going to show you something where, sorry that I'm speaking through the problems, because I'm not doing anything other than basic algebra that you guys should know now. Number 17. If they don't do an error analysis question where they treat this as multiplication, I'm going to kind of do one within them for you and say this is what students often do. This is a trap you cannot fall into. Function notation, notations are just the way things are written. That doesn't necessarily mean that they follow the exact rules that you're generally used to seeing. That's actually the same for inverse notation. Not that you know anything about that. But inverse notation also doesn't follow the rules of what you normally think about with negative exponents. Negative 4 plus 3 is negative 1, and I want to multiply both sides by negative 2 for this one to get rid of that negative 1/2, and now I have x equals positive 2. Positive 2 here. Last one, number 18, we have y equals negative 4/5 x plus 7, and we want to find out what value of x gives us a y value of negative 5. That is exactly what this problem says. It doesn't matter that it says j of x right there. That still means y is a function of x. So we're substituting -5 for j of x. Whoa. I'm going to subtract 7 from both sides, and then we're going to solve for x here. We got -12. What input would get us an output of -5? I do wonder. Let's multiply by -5/4 to figure that out. Then they'll tell us. They'll show us. We'll see. We'll see. Give me 1 second. This was not a -1/2. This was a +1/2. I was looking at the number and I said, wait, did I get a positive answer? I'm sorry. Let me go back. Maybe I shouldn't be talking over problems. So I'm multiplying both sides by +2, and that gives us a -2. Now that's something that, hey, please catch on to it on your own, right? I may be a solution guide and I may have faults. That's one of them, and I did address it. Because when I looked back up and I said that's positive. Don't just go, hey, why did he turn it negative? Oh, well, I guess I'll do that. Trust your own actions. Question your own beliefs on that situation. Anyway, this was negative as I'm looking at this. Because what I was asking myself was, why did they have 2 negatives in a row? And then I went back and I said, oh, they didn't. Anyway, sorry about that. 12 over 4 is 3. 3 times 5 is 15. Negative times negative is a positive. So x equals 15 in that case. If I made any other mistakes, it's too late for me to check. I have no idea. I don't think so. Problem was I was talking through the other problems. Just like when I have typos. Because I'm talking through things. All right, in exercises 19 and 20, find the value of x so that f of x equals 7. Now, 19 and 20 are visual version, right? They're graphs. So if they said, and it's interesting that they're giving you this first without giving you the other version. If they said find f of 4, f of 4 says find the value of y when x equals 4. Oh, it would be this number. I guess it's not a perfect number, so that's a bad example. But they're saying find the value of x so that f of x equals 7. F of x means y. Y is equals 7 is right here. What value of x is that? 5. So on number 19, f of x equals 7, x equals 5. There's a point on the graph that's 5, 7. That's what we're trying to find. Number 20, find the value of x so that f of x equals 7 here. The y value of 7 is right up here where that arrow ends. That is an x value of -3. So for number 20, when f of x equals 7, the x value that comes from that is -3. Quick. Normally for graph examples, and I'm surprised they didn't do it, but normally they'd ask, hey, what's f of 3? And they'd say, oh, it's this number. I'm giving bad examples because those aren't hitting integer values. Number 21. The function c of x equals 17.5x minus 10 represents the cost in dollars of buying x tickets to the orchestra with a $10 coupon. So the minus $10 is already accounting for the $10 coupon. We're taking $10 away from your cost. So c of x, 17.5x minus 10. So I want to buy x amounts of tickets. This will be my cost. How much does it cost to buy 5 tickets? Part A. So the way that I respond to that is I do c of 5. The cost of 5 tickets is represented by doing 17.5 times 5 minus 10. 17.5 times 5, I don't want to mess up, so let's get it. I believe it's 87.5. Let's see, 17.5 times. Yep, 87.5. 87.5 minus 10 is 77.5. That's $77.50 for 5 tickets. That was C of 5. I don't even feel I need to write the whole cost of 5 tickets anymore. We know what C of X represents. We know that C of 5 is the cost after 5 tickets. That's what I like about function notation. Part B, how many tickets can you buy with $130? This time we have to make our C of X represent $130, and we have to find what value of X would make this true. So now we'll say $130 equals 17.5x minus 10, and we solve for x in that scenario. So if I add 10 to both sides, I get 140, and this does divide evenly. I have to come up with it. Give me 1 second. 17.5. This is I think 8. So x equals 8. 8 in that scenario. 8 tickets. 8 tickets. In that scenario. Number 22. The function d of t equals 300,000 t represents the distance in kilometers that light travels in t seconds. 300,000 kilometers a second, yo. Science. How far does light travel in 15 seconds? Well, let's start with this. D of t equals 300 thou t. Blink and you'll miss it. All right, part A. D of 15. How far is the distance after 15 seconds? 300,000 times 15. That's going to equal, basically 3 times 15 is 45, so I can put a 45 there with these zeros. And like that. 4,500,000 kilometers. 15 seconds later, 4,500,000 kilometers. Part B, how long does it take light to travel 12 million kilometers? This is where our D of t, kind of like your y, is 12 million kilometers, and we need to substitute that for all of D of t and solve for t along the way. 12 million equals 300,000 t. These are the ones where I make the most mistakes on if I try and solve mentally, but I'll still try and give it a shot. I don't want to be wrong. This would be equivalent to, if I take away the zeros, this would be equivalent to 120 divided by 3, which would be 40. So I believe it's 40 seconds, which makes sense within the context of this thing. 40 seconds for that. Exercises 23 to 28, graph the linear function. Now, what they did previously was they used a table. Let me actually pause to get the table made. Hold on a second. All right, guys, I'm a crook. I'm a thief. I stole their table. I used this template, and I whited out their f of x values. So, all right, we're going to use this for our problems, and we have 6 of them to do. So it's going to take a little bit of time, but I'm going to speed up through the substitution of values. And over time, we're going to learn a little bit more about what we do here. So p of x equals 4x. We have to take, remember, this is now p of x. Okay, I got to change that. X and p of x. We got to take p of negative 2, which means 4 times negative 2. That's negative 8. So negative 8 goes in here. P of negative 1. So listen, that's what we're doing. Substituting these for x, getting these for y, right? Listen, we did this last section. We just didn't use function notation, but p of x, p of negative 2, p of negative 1 is negative 4. 4 times 0 is 0, and 4 times 1 and 4 times 2. So those are the values that we have for this set, and we still have to sketch its graph by plotting these points on here. What we need to remind ourselves of, let me grab one. What we need to remind ourselves of while doing that is that p of x just means y. So these are ordered pairs on a graph just like any other table set would be. So, although I can't really fit everything perfectly, I'm going to have to shrink a couple things. So like this is all we can see. We have a point that's negative 2 for x, negative 8 for y, negative 1 for x, negative 4 for y, 0, 0, 1, 4, and 2, 8. Now, I mentioned this in the lecture portion as well, but guys, our domain is not restricted here. We can plug in any values for x, get any values out for y. We choose clean values for ourselves to help assist us in our graph, but we do connect the dots. These have all real number domains. So that means that, and they are continuous. So that means that any value can exist in between. I could have plugged in p of 1.3. I could have done p of 17. I could have done anything here and it would have satisfied it. And there's my graph. Number 24, h of x equals negative 5. Now this one's interesting. It's the first of its kind that we've seen. I will still steal the table. But I want to, as I do that, I want you to make sense of what this is here. First of all, it's in y equals mx plus b form. Now, when you think about it, this is y, right? Where's x? It's not here. What we said for that is that means it's being multiplied by 0. Here's the plus b, this minus 5. That means if I substitute values into here, 0 times x minus 5, and I take, h of x is here, what happens if I do h of negative 2? Well, that's 0 times negative 2 minus 5. 0 times negative 2 is 0, minus 5 is negative 5. What if I do h of negative 1? That's 0 times negative 1 minus 5, which is negative 5. H of 0 is 0 times 0 minus 5, which is negative 5. What's happening here? Remember, x is being multiplied by 0, or in some cases, x doesn't exist in here. Wait, Mr. Robinson, how do I plug these numbers in if I don't have an x? You don't, right? Here's the last thing you want to do. You don't want to say h of x is negative 5 and say h of 2 is negative 5 times 2. I'll go, whoa, wait a minute. Where did you just plug that 2 in for? I don't know. I just did it. You're supposed to plug it in for x. Where's x? There isn't an x. So what do? You don't plug it in. You don't plug it in. Or you write it as 0 times x, and you multiply it by 0, and then it goes away. You don't do anything. H of 1 is negative 5. H of 2 is negative 5. Remember what this equation is saying. It says y is negative 5. Regardless of what x is, y is negative 5, period. X can be any number. And remember, x is numbers. You can plug in numbers for x. They just don't plug in anywhere. That doesn't change your output. If we input any number in the world into nothing, y is still negative 5. What does that mean? It means there's a point that's right here, right here, right here, right here, and right here. And guess what? As a continuous function that would have kept going no matter what I plugged in for x, it would keep going like that. This is a horizontal line. It's a linear function. It's a horizontal line. And y equals constant equations will look like that. That's something that we're going to have to get used to over time. But there's a build into that. Number 25. Now this is where I'm going to get a little... I'm going to choose my values a little more wisely. I'm not just going to choose negative 2, negative 1, 0, 1, and 2 anymore because now I have a fraction. I would rather choose values because I can freely choose them. I'd rather choose values for x that would divide by 2. And 1 and negative 1 do not divide by 2. So this, I don't like this anymore. I don't want the, well, negative 2 was fine. In fact, 0 is fine. I'm going to keep that there. But I'm going to stretch this out a little bit more. I'm going to go by multiples of 2. Let's go 2 and 4. Let's go negative 2 and negative 4. I like that more, right? We're going to take half of these numbers. What's half of negative 4? It's negative. Is it negative 1/2? I don't want to mess up. All right, we're going to do this mentally, okay? When we do negative 1/2 times something, we're changing their sign and dividing by 2. So negative 4 divided by 2. Sorry, negative 4 divided by negative 2 is 2. 2 minus 3 is negative 1. Negative 2 divided by negative 2 is positive 1. 1 minus 3 is negative 2. Negative 1/2 is 0. 0 minus 3 is negative 3. Maybe you see a pattern. Half of negative 1/2 of 2 is negative 1. Minus 3 is negative 4. And negative 1/2 of 4 is negative 2 minus 3 is negative 5. You can see that constant decrease as this thing goes. But now x's are going by 2's, not by 1's. You can make them go by 1's, but then you have fractions. That's your choice whether you'd like to deal with them or not. I'm choosing not to. I have a choice. X is my independent. So when x is negative 4, y is negative 1. When x is negative 2, y is negative 2, and so on and so forth. These points go like so. I still draw a line through these. I'm going to fix it, no worries. But I still draw a line through these. And please use a ruler in cases like these. I should already stress this right now. In future sets, we're going to plot as many points as we can fit, meaning I'm going to keep going on this thing. I'm not done at that stage if I want to truly keep going. But because we're only plotting so many points on these things, I'd like to stress the fact that you should use a ruler and go as far through as you can and make sure that it still satisfies that set. Number 26, w of x equals 3/5 x plus 2. We continue our journey of fractions. This time they're dividing by 5. So what should I do? Choose increments of 5. You know what divides by 5 besides 0? 5 and 10. Negative 5 and negative 10. Let's get the graph ready first, just kind of get it there. And let's bring our table in. And let's wipe out some numbers, shall we? This is w of x this time, by the way. Oh, should have kept the 0. That's okay. All right. W of x. Okay, here we go. Negative 10, negative 5, 0, 5, and 10. And I can still fit those on my graph. Let's see if the y's match up. Let's start with 0 this time. 0 plus 2 is 2. 3/5 times 5, you divide the 5's, right? Is 1 times 3 is 3, and 3 plus 2 is 5. 10 divided by 5 is 2, times 3 is 6, plus 2 is 8. And these are negative 3 plus 2 and negative 6 plus 2, right? It's just multiplying those negatives by that. So we get negative 1 and negative 4. So these should be the points for the graph that we're going to plot. I'll kind of get those out of the way. I need to see what you... Okay, we only need to really look at mostly positive numbers here. So negative 10, that's at the far reaches of this, right? Negative 10, negative 4. Boom, all the way down there. Negative 5, negative 1. This spacing is probably even better for some of the values because you really get a good reach of what this is. We couldn't do it for like the first equation though, p of x equals 4x. If I substituted 10 for x, what would happen? I'd get y equals 40. I can't fit 40 on this graph, and I wouldn't bother wanting to change my scale, so it made more sense for me to just choose what I had. This one makes a lot more sense for something like this, and I don't have to deal with fractions. So I really like that one. Two more of these, not fractions, but they're not quite in our slope-intercept form either. That doesn't matter, but I like slope-intercept form. Number 27, sorry, y equals mx plus b form. I don't know if we're supposed to know that other phrasing yet. G of x equals negative 4 plus 7x. You know what? I like g of x equals 7x minus 4, personally. Now, what values of x am I going to choose? Just the negative 2 to 2. That'll work. Let me find one of my tables to copy and paste it. Copy, paste. Let me get another set ready on the side. All right, 7x minus 4. I got the values here. This is a g. What's this f doing here? Negative 14 minus 4. Negative 7 minus 4. 0 minus 4. 7 minus 4. 14 minus 4. So I can't, unless I change my scale of my values for y, I can't actually fit everything, which is, oh well, they just said sketch a graph. I can go from negative 10 to 10. I did what I could, and it looked okay. And now that we sketched this graph, we're going to see what we can fit. Negative 2, negative 18 don't quite fit. I'm just going to leave it. Negative 1, negative 11 doesn't perfectly fit, but I've fit worse. So about there. Maybe just a little bit over to the left. Negative, or 0 comma negative 4. Sorry, I have to bring this stuff up for you guys. 0 comma negative 4 is here. 1, 3. And 2, 10. It's a very tall graph in comparison to some of the other ones, right? Very, very sharp. Sharp increase on y. X barely increases by 1. And y is really shooting up there. Oh, this thing goes. And I don't know, you know, as much as we're doing graphs and you're practicing, I don't know if you're practicing function notation. Clearly, we're just substituting values, right? That's all it is. Inputs, get outputs. Maybe you start picking up on some of the behaviors of graphs, either in the table or what we do on the graph itself. And if you pick it up early, cool. If not, wait for the next section. We're going to learn some more as we go along. Rewrite this in slope-intercept form if you so choose. I so choose, so I shall. Negative 6x plus 3. Probably the same kind of thing. This will be probably a pretty tall graph overall. Let's check and see how that's going to look. Hey, we're back to f of x, by the way. So negative 6 times negative 2 is 12. Plus 3 is 15. Again, out of range. This will be 6 plus 3, which is 9. 0 plus 3. Negative 6 plus 3. And negative 12 plus 3. That one can actually fit. So once again, the negative 2 probably won't fit on these graphs that I'm providing for you. At least they're not that I'm providing for myself. So I can only fit 4 of the 5 points here. Just make believe on the other. That's what the line is for, right? With the arrows. It's there for that kind of reason. So negative 215, out of reach, somewhere high up there. Just make believe. I got negative 1903. 4 points is plenty. I would state plot as many points as you can fit anyway. This is plotting as many points as I can fit. I can fit 4 of them. I'm going to plot them. Like I said, it's another sharp graph. Goes a little downward as it goes right instead of up and right. But there's a sketch of that one. So I'm doing inputs, right? I'm doing f of negative 2. That means negative 2 is going in for x in this equation. And just, you know, that's it. That's it. All right, 8 more questions to go. Let's see if they are of the long or short variety. No idea. Number 29. Problem solving. The graph shows the percent p in decimal form of battery power remaining in a laptop computer after t hours of use. So you can see it's going in decimal form. This is the percent. So 1 means 100%. 0.8 means 80%, things like that. A tablet computer initially has 75% of its battery power remaining and loses 12.5% per hour. Which computer's battery will last longer? Explain. So they're showing one computer here, this laptop, and then we got to talk about a tablet. So the tablet, we can kind of make an equation. Listen, you can do a table, you can make an equation. Because of function notation stuff, let's do an equation. Let's do an equation. I'm going to call this tablet's equation t of x. What it's going to mean, oh, shoot, hold on. They're already using t for that. Okay, I can't use that. Let's call f of t. F of t, they have p of t for its power. F of t will be the tablet's power. I hope that's okay. So what's going to happen is it currently has 75% of its battery power. That's 0.75 as a decimal. And then it's losing 12.5% per hour. So it's losing, boom, like that, times t. It's weird as decimals. We can probably turn it back into percentages we want to. They said, which computer's battery will last longer? I want to find out for what value of t. I mean, we could do this on the graph. I prefer the equation. We want to find for what value of t do we get a battery power of 0. So I'm going to substitute 0 for f of t, and we're going to solve for t in this equation. There's more than one way to do this, guys. I believe the book, the lecture, did this 2 different ways as well. They did it on a graph, kind of in a table. But I want to use function notation. I want to do this beyond what we're talking about. So this is what we did. So I'm going to add 0.125 t on both sides like this. That's 12.5% that was being decreased over that time. So 0.125 times t equals 0.75. If we divide both sides by 0.125, and I think that cleans up because 12.5 doubled is 25, 25 tripled is 75. So that would be 6 times more. So that would mean t is 6. This would take 6 hours for the battery life to deplete on the tablet. Now, when p of t is 0, the t value is 5. If you guys look at that table, the graph, after 5 hours, it depletes to 0%. So 6 hours versus 5 hours. They say which computer's battery will last longer? The tablet will last longer. An hour longer than the laptop. Now, what's interesting about that is it also started at 75%. The other started at 100%. So that tablet battery life is pretty good, 12.5% per hour. How much is this losing per hour, by the way? This is losing 20% every hour. Every hour. So 12.5% versus 12%, man, that's the difference. Excuse me. Number 30. The function c of x equals 25x plus 50 represents the labor cost in dollars for certain. By the way, was there an error analysis? I'm sorry. Was there an error analysis question? Let me quickly check. We didn't have an error analysis thing. I just realized that. All right, anyway. Unless we did and I totally forgot. The function c of x equals 25x plus 50 represents the labor cost for certified remodeling to build a deck, where x is the number of hours of labor. So x is there, 246. The table shows labor costs from its main competitor. Oh, I'm sorry, that's the table versus this one here. The table shows sample labor costs from its main competitor, Master Remodeling. The deck is estimated to take 8 hours of labor. Which company would you hire? Explain. Okay, so in this one here, I'm going to copy and paste that table. We have 2 different things going on. I'm going to call this one, because I can give it some variables. I'm going to give this one an M of X. This is C of X for certified remodeling. This one's called Master Remodeling. I'm going to call this one M of X. Based on our X, this is our M of X stuff. Now, you can either come up with an equation for this, which we're probably not yet attuned to do. You probably could if you learn more stuff about it. Or we could just figure out what hour 8 is based off the difference here if it's constant. And it is. Here we're adding $60 every 2 hours. So another 2 hours later, we're going to add another 60. And $60 later would be, or $60 more would be $250. So when it said, which company would you hire? Assuming all things equal when it comes to building the deck, if they build the deck the same way, which one do you want to spend less for is what they're asking. Now, in this case, we want to do C of 8. If X is the number of hours, 25 times 8 plus 50. 25 times 8 is 200. So 200 plus 50, okay. 200 plus 50 is 250. So no matter which one you go with, you're going to spend $250. So I guess that just depends on which one you want to do. Because this is adding $60 each time. Wait, did I do anything wrong there? 25x plus 50. Deck's estimated to take 8 hours of labor. Which company would you hire? I did everything right? So they're both equal at 250? Let me make sure I didn't write anything wrong. Give me a second. Dude, I totally messed up on this other thing for Master Remodeling. I'm like, why would they have it spend the same? That's not plus 60 each time. I must have looked at something wrong. I don't know what it was. If I looked at 60 and said plus 60, if I saw this and said plus 60, I apologize, guys. That's plus 30 and plus 30. Again, if you catch that before me, go for it, right? It's whatever. I don't edit out my mistakes. They are what they are. All right, this is $220. Got it. Okay, 250 versus 220. I'd rather go with master remodeling because I'm going to spend, $30 less. So, master remodeling. Because I would spend $220 for 8 hours of labor as opposed to $250. Assuming all things are equal. All other things are equal. Right? They do the same good job, that kind of stuff. Okay, number 31. Making an argument. Let P of X be the number of people in the U.S. who own a cell phone X years after 1990. Your friend says that P of X plus 1 is greater than P of X for any X because X plus 1 is always greater than X. Is your friend correct? Explain. All right, well, this stuff gets a little, hold on. Number of people in the U.S. who own a cell phone X years. They said, your friend says P of X plus 1 is greater than P of X because that. Okay. Now, your friend may be correct as an overall as far as truth of the matter. What your friend is stating, though, is possibly poor logic. It depends on the situation. When my friend states the above, they are assuming that just because it says X years after 1990, just because we look at later years, we look 1 year later. See, P of X plus 1 means, or X plus 1 means 1 year later than X. Just because we look 1 year later after year X, that there would be more cell phone owners. He's likely right, or my friend is likely correct, but you cannot assume this. But this cannot be assumed. Functions can definitely decrease. Just because X grows doesn't mean P of X has to grow, or whatever, right? Just because your input gets bigger doesn't mean your output has to get bigger. For this particular situation, I'd probably agree. I'm recording this in the year 2024. In 2025, there will probably be more cell phone users than there are in 2024. Technology, population, access, but expenses, right? They're cheaper. People who normally get a cell phone don't often normally stop using a cell phone too, right? It's just once you get somebody on a cell phone, that's it, unfortunately. But right, so they're probably right, but you don't know anything, right? We had the customers in the restaurant. We had there are different things like that happen. So it just depends. In this situation, my friend's not necessarily correct. Number 32, thought-provoking. Let B of T be your bank account balance after T days. Describe a situation in which B of 0 is less than B of 4 is less than B of 2. Well, that's a perfect follow-up to the friend one, just as far as the fact that just because more time goes on doesn't mean you have more money, or the other way around, right? So what would make B of 0 be less than B of 4 be less than B of 2? Now, this is after T days. So what this tells you is that this is not telling me the situation. Excuse me. This is not me answering the question. This is me interpreting what this is saying. This is saying on day 0, or today, whatever. On day 0, that's the only way I can say it. On day 0, I have less money than I do on day 4, which is less than on day 2. That means I had the most money on day 2. I had the least on day 0. So what could happen? Let me type this. I could receive a paycheck. I could have some money to start. And then, hold on a second. And then on day 2, I could receive a paycheck. And by day 4, I could have spent some of that money. Or withdrawn some of the money, really, but received a paycheck, deposited, right? Because This is what happens first. This is what happens second. This is what happens third. Time goes from 0 to 2 to 4. The money amounts do not go from money on day 0 to money on day 2 to money on day 4 because money on day 2 was the most. All right, number 33, mathematical connections. Rewrite each geometry formula using function notation. Evaluate each function when r equals 5 feet, then explain the meaning of the result. So diameter says d equals 2r. Now there's no reason for us to not be able to just say d of r equals 2r. This is a way of allowing us to see what our input is here when we want to find our certain output. This is the diameter given a radius equals twice your radius. So let's do diameter with given a radius of 5. That's 2 times 5, which is 10. What this states is the diameter, when the radius of a circle is 5, its diameter is 10. I can probably fit that there. Okay. When the radius of a circle is 5, its diameter is 10 units. They don't really say what the units are, so I'm just going to say units. Oh, did they say it? Oh, 5 feet. I'm sorry. 5 feet, 10 feet. Okay. Sorry about that. All right. That's part A. Part B, area. A equals pi r squared. Let's write that as A of r equals pi r squared. This doesn't mean A times r. This means substitute r, 5, there's radius, given, substitute a radius and get an area. So this will be 25 pi square feet. By the way, this was feet. 25 pi square feet. What this means here is that when the radius is 5 feet, the area of the circle is 25 pi feet. Of a circle, whatever. Its area is 25 pi feet. I don't have the pi button here. Actually, I might. Let's see if I can find it. Sorry, I want to be picky. Do I have pi here? There it is. Pi. Okay. Part C, circumference is 2 pi r. C equals 2 pi r. Well, not anymore. We're going to say C of r equals 2 pi r. And let's do C of 5. That's 2 pi times 5, or 10 pi feet. I don't know if we're supposed to be rounding these ones. Did they say? Not really. But 10 pi feet's around 31.4 because it's 3.14 times 10. So when the radius of a circle is 5 feet, its circumference is 10 pi feet. I'm going to steal you. Thank you. All right. Okay. 3 more questions. Numbers 34, 35, and 36. Got a little Nike swoosh there. Number 34, how do you see it? The function y equals a of x represents the attendance at a high school x weeks after a flu outbreak. Once again, y equals a of x is just saying a of x and y are the same thing. Here's your y, here's your a of x, whatever. The attendance at a high school x weeks after flu outbreak. So flu outbreak, you're losing students, then they start slowly trickling back. What happens? Oh, so that's part A. What happens to the school's attendance after the flu outbreak? Well, you dramatically lose students over the course of some time. I don't know if we have to be specific about numbers, but the attendance after the flu outbreak, the fly outbreak, after the flu outbreak, the attendance, it rapidly decreases for a moment. And then it slowly decreases back up. Then slowly decreases back up. It slowly increases back up. Decreases. Decreases up. I don't know what that means. Part B. Estimate A of 13 and explain its meaning. So yeah, this is one where we get to actually check it on the graph. A of 13 means when x is 13, what is y, right? So we look at 13. This is 2, 4, 6, 8, 10, 12. 13 would be right here in between. So I'm going to go up, up, up. And look, that's about halfway between 400 and 450. I'm going to say 425. So A of 13 to me is about 425. Now it says interpret, explain its meaning. To me, this says 13 weeks after the flu outbreak, there's an attendance of 425 students at school. How do they say it? At school. This is one of My high school is not quite that small. So 13 weeks after the outbreak, the flu outbreak, there are approximately 425 students at school. So that's what we're doing there, right? There's no equation for this that we necessarily have, but we're looking at input and output. There's the output based on that input. Part C says use the graph to estimate the solution or solutions of the equation a of x equals 400. Explain the meaning of the solution or solutions. They're probably hinting at something when they say solution or solutions. This says the y value is 400 students. What weeks do they have 400 students? And there can be more than one. It can function that way still. 400's right here. So 400, what x value is that? And let's move this one over. 400 here, what x value is that? I'd say, because these go by twos, I'd say that's about 1 week in. I'd say here, x can equal 1. Why is there a comma? X can equal 1, and x can equal about 10. 10. So to me, this says, given that output of 400, there were 400 students at school. Both 1 and 10 weeks after the outbreak began. I don't know if we say just the outbreak or the outbreak began or whatever. The flu outbreak. Part D, what was the least attendance? When did that occur? Ooh, things like minimum things and stuff like that. That happens more in IM2, but we can read that. What was the minimum attendance? About 350 students, right? When did that occur? Week 4. The minimum number of students was 350. This was 4 weeks in. Sorry, the minimum attendance was 350 students 4 weeks after the outbreak began. Part E, how many students do you think are enrolled at this high school? Explain your reasoning. I'm probably going to say, hold on. Listen, students are always going to be absent in certain things, right? Even before the flu outbreak, it's not that there's maximum attendance. Some people are going to be absent. I don't know how many people are absent in school. There could be as many as 20% on a given day. I'd say probably 500, right? There's 400, 450, 500. Now this starts actually, I don't know if you can tell, this isn't hitting 450 right here. This probably hits about 450 right there, or just under. This hits a little over 450, but that's before the outbreak. I'd say maybe, listen, if that was at 460 or so, to have 40 students absent, maybe there are more in general. I'd say maybe there are about 500 students in the school. I don't know. But I'd say, I don't know, about 500. They said explain. The idea is that not all students would be present at any given day, outbreak or no. Whether or not there is an outbreak. So the fact that there were about 460 students in attendance before the outbreak, or at the time of the outbreak, before the outbreak means some students, I don't know, around 10-ish%, right? A small portion of students would be absent. Anyway, that's my guess. I don't know. Sounds good. I like it. All right. Number 30. Let me bring down the thing. Number 35. Interpreting function notation. It says let f be a function. Use each statement to find the coordinates of a point on the graph of f. This is one of the first things that I called out in the lecture, actually, what f of x meant and how it works. When it says f of 5 is equal to 9, this is part A. You separate that. A. F of 5 is equal to 9. That means when x is 5, y is 9. That means that there's a point on the graph that's 5, 9. That's literally what that means. Part B, a solution of the equation f of n equals -3 is 5. That means that n is 5 there. That means this is your input and that's your output. Input of 5. That also means f of 5 equals -3. So this has 5, negative 3. Now, what's interesting for this right here is, I guess these would be two different functions. It says let f be a function, but literally, what's kind of interesting about this is literally what a function wouldn't do, where you could have the same input and different outputs. So I'm assuming these are two completely independent problems, not related to each other, despite the fact they use f each time, f of this. They actually, I guess, mean two different things. Otherwise, they screwed up their own problem. Anyway, number 36 says, given a function f, tell whether the statement f of a plus b equals f of a plus f of b is true or false for all inputs a and b. If it's false, explain why. I know the answer, but I want to think about what things you would know and not know, or what things we could talk about that we already learned. What this states is that if I just add my two input values that I have and evaluate its output, that's the same thing as if I evaluate the output for the two separate inputs. Let's think about, but before I do actual math ones, and I'll do a pretty common math one that I do at least for IM2 students. Let's think about the like the restaurant example, right? Let's say that F was the number of customers in the restaurant after 3 hours after 6 or at X hours after 6 a.m., right? Or A hours. So if I did, here's 3 hours after it opens, there are 20 people in the restaurant. And 5 hours later, there are, 32 people in the restaurant. Does that mean that this would be, see, when we're saying this, now we're saying this equals f of 3 plus f of 5. Is that for us to then say that f of 8 would be 20 plus 32, that 8 hours later we'll have 52 people in the restaurant? Is there any guarantee of that? I mean, just in terms of logic? Now, you'd say no for that, right? Now, I don't know what kind of equation we have to represent that. It's clearly not a linear equation. Well, listen, if it was a linear equation, then maybe that would be the answer. Maybe. Maybe not. There are different things that could happen all based on that. But we don't go off that logic, right? So that's what kind of says that no, this doesn't work that way. Now, let's do one that actually has a math basis to it that I speak for IM2 on all the time, which is quadratic equations or square root equations. Let's look at some f of x equals x squared scenario, quadratics, because people seem to believe that if you square a plus b, that's the same thing as doing a squared plus b squared. Well, let's figure out if that's true. Big old question mark on that one. Let's test whether f of 3 plus 4 equals f of 3 plus f of 4 in this equation. Because this is all based off that a plus b squared is a plus, all that. So let's try f of 7 and compare it to f of 3 plus f of 4. Now, let's evaluate them. F of 3 equals 3 squared, which is 9. F of 4 is 4 squared, which is 16. And f of 7 is 7 squared, which is 49. The question is, does 49 equal 9 plus 16? No. No, it does not. As to answer the question, does a plus b squared equal a squared plus b squared? No, it does not. Quadratic equations do not have this thing here. So, is this true for all inputs a and b? No. I'm explaining through counterexample here. There are certain functions that do not allow this to be so. There are certain functions that do, and there are some that don't. No, this is not true for all function types. As if to say that you can just kind of distribute this function thing into these individual parts to make that happen. Absolutely not. Absolutely not. There are some that work, but disproved by counterexamples is the way I went with that. And guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Coming up, because this was 3-3, right? So coming up after this will be a 3-1 to 3-3 quiz where we had a variety of things, a lot of new terms, a lot of new visual representations, brand new notation here in function notation, but it doesn't change how we do what we do. We just got to make sure that we can analyze it properly and utilize it the way it's supposed to be. I hope this video helped. Thank you so much. Take care. I'm going to see you in the next one.